Have you ever stopped to think about how the actual effort you put into something, pushing, lifting, running, how that actually turns into a real, measurable effect in the world? Well, that's exactly the story we're going to unpack today. It's all about the physics of getting things done. So let's just dive right in.
Okay, so picture this. You're pushing against a solid brick wall with everything you've got. You're sweating, your muscles are screaming, you're completely exhausted. And yet, physics says you've accomplished absolutely nothing. Zero work. How on earth is that possible? Well, that's the exact puzzle we're here to solve.
The whole paradox, it all comes down to one simple, maybe kind of strange idea in physics. Your effort, the force you're applying, it only counts as work if you actually succeed in moving something. If there's no movement, there's no work. It's really as simple as that. So let's get the official definition on the table. Think of work like a recipe with two key ingredients: force and distance. It's the energy that gets transferred when your force actually makes an object move over some distance. You have to have both. If one of them is zero, well, you didn't do any work. That's the rule. And of course, in physics, we love to put a number on things. The equation for this is beautifully simple. Work done is just the force you apply multiplied by the distance the object moves. F times d. And believe me, this simple little formula is the bedrock for everything else we're going to talk about. And just like that, our opening puzzle is solved. This person is pushing a boulder with 2,000 newtons of force, and that is a huge amount of effort. But the boulder doesn't move an inch. The distance is zero. So you have this massive force times zero. And what does that equal? Zero. Absolutely zero work done. Okay, so that's what doesn't count. Now let's look at a case where work is actually done. Here we've got a crate. We're using a much smaller force, only 20 newtons. But, and this is the crucial part, we actually move it. We push it 5 meters across the floor. So we've got our two ingredients, right? Force and distance. Let's do the math. So 20 newtons of force times 5 meters of distance gives us 100. 100 what? 100 joules. A joule is our standard unit for both work and energy, really because they're two sides of the same coin. When you do 100 joules of work, you are transferring 100 joules of energy. All right, pushing things horizontally is one thing. But what happens when we do work vertically? When we lift something up against the pull of gravity? Well, that leads us to a really cool idea: storing the work you've done as a totally new form of energy. What's so great about this is that potential energy sounds like some brand new complicated concept, but it's not. It's actually just our good old work formula wearing a disguise. We start with our familiar work equals force times distance. But when you're lifting something, the force you have to fight against is its weight, right? Which is just its mass m times gravity g. And the distance you lift it? Well, that's just its height, h. So you just swap them in. F times d becomes m times g times h. Let's make this real. Imagine you take a 2.5 kilogram football and you do all the work to lift it to the top of a 180-meter high cliff. By doing that, you have literally packed it with 4,500 joules of what we call gravitational potential energy. It's just stored energy, sitting there, waiting, all because of its new position. So, we've done the work. We've stored up 4,500 joules of energy in that football by putting it on the edge of a cliff. The next obvious question is, what happens when we just let it go? This is where we meet the other side of that energy coin, kinetic energy. If potential energy is the stored energy of position, that's our football waiting at the top, then kinetic energy is the released energy of motion. That's the football as it's falling and picking up speed. You're literally watching stored energy become active energy. And here's the formula for it. Kinetic energy is 1/2 of the mass, m, times its velocity, v, squared. Now, I want you to look closely at that v squared part. That little 2 up there, that is the most important part of this whole equation, and it has some massive real-world consequences. So why is that squared term such a big deal? Because the link between speed and energy isn't just a straight line, it skyrockets. Think about driving a car. If you double your speed, say from 30 to 60, you don't have double the energy to deal with in a crash. You have 4 times as much. Your stopping distance quadruples. And if you triple your speed, you're dealing with 9 times the destructive energy. That v squared is literally why speed is so critical. Okay, let's just recap. We've connected force and distance to get work. We've seen how that work can be stored as potential energy and then released as kinetic energy. Now it's time to add the final ingredient to our story, time. And that brings us to the idea of power. Power is all about speed. It's a measure of how fast you're doing work. If you and I both lift the same 10-kilogram box onto the same table, we've done the exact same amount of work. But if you do it in 1 second and it takes me 3 seconds to do it, well, you're 3 times more powerful. It's just the work done divided by the time it took, and we measure it in watts. Check out this great everyday example, someone running up a flight of stairs. First, you calculate the work they did against gravity, which we now know is the potential energy they gained. That works out to 3,500 joules. And they managed to do all that in just 7 seconds flat. So to find their power, all we have to do is divide. And the result is 500 watts. Now to put that into perspective, that's enough power to light up 5 of those old, bright 100-watt light bulbs all at once. Suddenly, that number gives you a really real sense of the physical effort that person was putting out.
So, we've covered work, potential energy, kinetic energy, and power. For this last part, let's bring it all home with the one golden rule of physics that connects every single one of these ideas into one beautiful picture.
And this is it. The law of conservation of energy. It's truly one of the most fundamental principles in all of science. It basically means that the total amount of energy in the universe is always constant. It just changes its form. It can go from chemical to potential to kinetic to heat, but it never ever just disappears.
And this is just a brilliant illustration of that law in action. Imagine a ball rolling off a table. The instant it leaves the edge, all of its useful energy is potential energy, our MGH. Then, as it falls, that potential energy gets flawlessly converted into kinetic energy, our 1/2 mv squared. The total number of joules is the same at the top and the bottom. The energy just changed its identity along the way.
Which brings us right back to our first calculation. And one last question to think about. We did 100 joules of work to push that crate across the floor. But once we stop pushing, it's not moving, so its kinetic energy is 0. It's not high up, so its potential energy is 0. So, if energy can't be destroyed, where did those 100 joules go? Well, the answer is they turned into other forms of energy we haven't talked about, like the heat from friction. And that's a whole other story for another day.